Welcome, everybody. As you continue to file in, let me get things started. I want to welcome all of you to our High Meadows Environmental Institute Faculty Seminar Series. My name is Mike Celia. I'm the director of the High Meadows Environmental Institute, and it's a great pleasure to welcome all of you back. As you know, we offer this seminar series the first Tuesday of each month, and all of our speakers are prominent Princeton faculty members. With today's speaker, of course, being Professor Stephan Fueglistaler. I'll remind you also that as we've done since we began offering these remotely, we invite anyone in the audience to submit questions using the Q&A box that you should see on your screen. You can do that anytime during the talk. I'll note that the chat function is disabled, so you should use the Q&A tab on your screen to submit questions. And as a reminder, the lecture is being recorded. As I said, today's speaker is Stephan Fueglistaler, with discussant being Jim Smith. I'll say a few words about Jim when I introduce him after Stephan's talk. But let me begin by just saying a very big thank you, an extra big thank you to Stephan and also to Jim. As some of you may have noticed, our originally scheduled speaker for today, Alison Carruth, unfortunately was unable to give her talk today. And it really was a sort of last minute email that I sent to Stephan asking if he might be able to fill in. And he was incredibly gracious in agreeing to be a last minute replacement. So, and I asked Jim even later than that. So I really want to thank Stephan and indeed both of them, both Stephan and Jim, for filling in so graciously and so kindly. All right, Stephan is a professor in the Department of Geosciences. He's also director of the program in Atmospheric and Oceanic Sciences, the AOS program on campus, which is a really interesting program. For those who don't know it, it is a collaboration between Princeton University and the Geophysical Fluid Dynamics Lab, GFDL, with members of AOS coming from both places. Really an interesting, unusual setup that works extremely well. Stephan is also deputy director of the Cooperative Institute for Modeling the Earth System, CIMES, and does a number of other administrative things related to AOS and other things on campus. Stephan himself is a climate scientist whose work focuses mainly on atmospheric physics. He works across a range of scales from, for example, very small scales looking at cloud microphysics to very large scale atmospheric dynamics and atmospheric systems. You may have read about some of his recent work. I know he'll say a little bit about this in his talk, looking at increases in temperature and humidity in the tropics and the possible implications on human health associated with that. Stephan has received a number of recognitions, including the NERC Advanced Research Fellowship from Cambridge University. He was the Miller visiting research professor at Berkeley, and he's held the Duesenberg preceptorship here at Princeton. Stephan is an associated faculty member in our institute in HMEI, and among many other things, he has initiated and organized the ongoing series of Monday afternoon lectures on climate science, which is jointly sponsored by AOS, the Department of Geosciences, and our institute, HMEI, but in fact, it's Stephan who does all the work for that and has put together a really fantastic series of lectures. And he has been a terrific friend in many other ways, including agreeing so graciously to step in and do this talk. So please, let's give an extra big virtual welcome to our good friend, Stephan Fueglistaler. Stephan, the screen is yours.
Okay, thank you very much for the nice introduction. I believe you should be able to see my slides. Is that correct?
Yes, it is.
Okay, wonderful. Okay, so thank you so much for the opportunity to present work here. I have a slightly long title, and I hope that over the course of the talk, it will become clear what I mean. And, you know, of course, the sort of the motivation for the whole talk is this curve. This shows carbon dioxide measured at the famous Mauna Loa Observatory in Hawaii. And it shows carbon dioxide in the atmosphere. And you see it's just going one way up. The curve starts in 1960, it's going to 2021, and it will probably continue to rise. We all know what the implications are. There is no doubt this will lead to global warming. There is no doubt about that. Where it gets more complicated is how much global warming and what exactly are the impacts of that global warming. The underlying theme of my talk today is, apart from showing you examples of what we're doing, is the importance that observation, simulation, and theory must evolve together in order to have reliable forecasts of what we are to expect in the coming decades. So what do I mean by that? I mean, theory is essential for the detection, attribution, and prediction of changes in climate. Without theory, we only get numerical results from a model, and we never know whether the next version of the model will give us a different answer. My talk today is focusing on the average and the extreme, typically the maximum. The reason why I'm talking about these things is usually it is simpler to predict the average change than the change in the extreme events. However, in many cases, we are more interested maybe in the extreme than in the average change. So as an example, I have here listed the situation in Princeton in summer. It gets very hot, right? And many of you complain about that. And if you do that, it doesn't help you to know that the average temperature in Princeton is about 57 Fahrenheit. Then you wouldn't bother if it gets a little bit warmer or colder. What really matters is how much will the temperature in summer change. We express that as a probability density distribution function. So on the x-axis, we would have the intensity of whatever event we're looking at. This could be temperature, but it could also be rainfall intensity, or it could be a storm intensity. And on the y-axis, we have a frequency distribution. How often do these events occur? And so the black line sort of just very schematically shows, for simplicity, I've taken a Gaussian just for the sake of the example, of a distribution that we would have in the present climate, the black distribution. So there's a mean, there's an average here, and a mode, and then we have a tail. And it's the tail here where we would have the extreme event. So that could be the hot days, for example. If we go to a different climate, to a warmer climate, for example, we would have maybe a distribution like this red, where simply everything is shifted by the same amount. So maybe just every temperature just gets 1 Fahrenheit warmer. If that was the case, then we would have an easy prediction of the extrema, right? Because we know, once we know what the mean is doing, we know what the extrema is doing. However, it may also be that as we change the mean state, also the distribution function, the shape of that function might be changing. And I've sketched that here with this orange curve here, where you see that this has a wider tail. So that means simply that if the future was more like the orange than like the red, the mean temperature change or intensity change would be the same, but we would have more extreme events. A prominent example of such a function shape change, for example, is the Planck blackbody spectrum. We know exactly what that spectrum looks like as a function of temperature, of the distribution of the frequencies of the emitted photons, and we know that this shape is changing. We have a theory for that, so we know exactly what the tails are doing. In climate, in most cases, we do not have an equivalent theory, and so we must rely to some extent on model simulations. And that makes it hard to put confidence in the tail here. But it is exactly this tail here that we are most worried, and that will cost us most. In my talk, I will present work that has been carried out in my group. And in particular, I'd like to acknowledge three. Yi Stang, whose work on heat stress really has hit the headlines recently. And I have you here sort of from a number of online screenshots that I could take that is talking about her work. We will start in summer in Berkeley with a prestigious Miller Fellowship for the postdoctoral work. I will also show work from Aaron Match, who is also a graduate student with me, and from Levi Silvers, who is a former AUS postdoc, who is now at Stony Brook. So let us start with Aaron's work. What I show you here is the black curve, is a time of change or of intensity of winds in the stratosphere. The details we need not to worry about. It's in the tropical stratosphere, it's high up, that's between 20 and 30 kilometers altitude. But what it shows in black is the observed intensity of these winds. And what you see is there's a lot of wiggle, but there seems to be a decrease over time. And the red line is sort of a rough trend line, and people have done that and made it to the journal Nature in 2013, claiming that what we see here is climate change. Why did they claim so? Well, statistically, this trend was robust, and model simulations predict a change with the same sign for the future of the intensity of these winds. We did not quite believe that this is climate change. And so Aaron went and developed a theory. How should these winds change under global warming? And the result is the red line. And what you see, they do not agree very well with the observation. So there's two things that can be wrong, right? And the one possibility is the theory is wrong. The other possibility is what we see is not climate change. So Aaron went and took a theory and compared it to model simulations. And forgive me, there are two lines here. The black is what the model predicts for the next 150 years. And each plot is a different model. So each model differs in their representation of these winds and differs in what they predict how these winds will change. Aaron applied his theory, and I said there are two curves, the red and the green curve. Please don't bother about the details. That's simply, the first one is the linear and the second is the quadratic expansion of the theory. So look at the quadratic, that's sort of generally the better. And the point is, Aaron's theory explains these model predictions very well, and it does so even if the different models give different predictions. So we do have some confidence in the theory, and with that we can go back to the observations and say, well, maybe the sign is as expected, but most likely what we see here, the attribution is not correct. The change that we saw was not due to climate change, but due to internal variability. And look, I've added here at the end the winds in the last couple of years, and they resorted back to the same level as we've had in the past. So I hope with this example to make it clear just how important it is to have a theoretical prior or backdrop against which you can compare your simulations or your interpretation of observational data. Well, now we zoom on to the impacts and the extrema versus the mean. Why do we care about the extrema? I've already mentioned impact. The second thing is, that kind of makes it interesting, in many cases, the atmosphere or the climate operates, the important processes operate when it is not in the average state, but when it's in an extreme state. Again, think of, for instance, in summer, the deep convection storms that develop, they will develop in the late afternoon when the temperature is way above average and the humidity is way above the daily average. So the air that gets exported is not equal to the daily average temperature over Princeton, but it's the temperature that you have when it is warmest. We took that idea to the tropics, where indeed you can think of deep convection more or less being solely responsible for the overturning circulation. So you need not think about mid-latitude eddies. And the question then is, of course, well, is it also true that in the tropics, some regions are colder, some are warmer, that deep convection happens over the kind of warmest regions? So the idea is in this sketch here is you have over the ocean, if somewhere it's colder and somewhere over the ocean it's warmer, and you would expect to deep convection over the warmest waters. This is indeed the case. What I show you here is a sketch or data where I bin the sea surface temperature from cold to warm, and I simply plot you the mean cloud top height. And a deep storm has a high cloud top height, and low clouds, what you have here, these shallow marine stratocumulus clouds, they are at low altitudes. So it's true, deep convection, the storms happen primarily on the warm end of the sea surface temperature distribution. There is something really odd happening with clouds. Clouds are the largest uncertainty when we look about climate forecast of temperature. Simulations of clouds are really, really difficult. So we rely on model simulation. What people have noticed is that if you run an atmospheric general circulation model, this is a model that simulates all atmospheric processes as good as it gets. But instead of coupling it to an ocean that tries to simulate what the ocean is doing, you simply prescribe the observed sea surface temperatures as lower boundary condition, and you observe what the model is doing with the clouds. When you do that, you get a very perplexing result. What is shown here is the time evolution since 1875 or so, a paper that we recently published, and these are results with the GFDL model AM4. So that's the geophysical fluid dynamics laboratory that Michael has mentioned before. And what it shows is the radiative effect of these clouds in terms of reflected shortwave, so that's solar radiation. And what you see is over the last decades, since the late 1970s, reflected solar radiation has massively increased. This is not what you get when you couple a model to an ocean. Then the result is more like this beige curve. This is what you would expect based on global mean warming. So something is happening here. It's very disturbing because, as I said, a coupled model is not doing this behavior. So what's going on? What's going on is exactly, again, the question of the extreme and the average. But this time we have a twist in that the extreme triggers a process which feeds back on the average. And what is that? Well, we've already said there are low clouds over the cold waters and there are high clouds over the warm waters. These low clouds, they know about the temperature difference between what we call the boundary layer, so that's the lowest layer of the atmosphere, and the overlying free troposphere. The idea that we have is that the deep convection is filling the overlying free troposphere with air, with temperature and humidity from the warmest regions. And so the contrast here reflects to some extent the contrast between here and here. So you have a contrast in space that translates into a contrast of temperature in the vertical. In the observed sea surface temperatures, you do not have perfectly even warming. It turns out that the warmest regions are warming more than the cold regions. And with that, this temperature difference gets larger. These clouds, they like this temperature difference. If you have a larger temperature difference, you have more clouds. And that explains what these simulations tell us with observed sea surface temperatures. And they tell us uneven warming leads to a feedback onto clouds. These clouds would actually reflect more sunlight. So that would actually mean you would have less mean warming. And you can see that this is disturbing because models don't do it on themselves if you couple them to an ocean. So the question is, where is that coming from? And it could be, again, that it is a so-called transient or internal variability effect, just like we've seen before. The climate likes to swing between different states. And even over 50 years or so, maybe it was shifting a little bit more from one state to the other, but that would mean it would eventually swing back. If one believes that this has happened, then we would have seen over the last few decades an effect that is countering the warming from CO2. If that system swings back, it would mean we would see in the coming decades more warming than the models predict. So we really need to work out what is happening here. It actually turns out that it's not so easy to even predict or reconstruct the observed temperature changes, which, as I said, this is the gold standard. Ultimately, the models must be able to reproduce the observation. The problem, as said, is this internal variability could mean that the climate has taken a rather unusual trajectory, maybe, and the models simply do not capture that trajectory in terms of these swings around the mean state. It doesn't mean that the model is wrong, but it just doesn't get that variability right. What I show you here is a recent paper that we published in PNAS. And what you see is on the y-axis is the temperature trend since the late 1970s. I explain the x-axis in a moment, but what you see is the temperature trend of the tropical troposphere. And this box here is roughly the observed range. So it's between 0.1 and 0.2 Kelvin per decade. First, I would note, this is actually quite a large uncertainty. I think it's a factor too. But what is even more disturbing is that when you look at the model simulations, most of them, but not all, but most lie outside of this range. What we plot here on the x-axis is the simultaneous change in the El Nino state. And you've probably all heard about El Nino at some point in your life. This is a large oscillation happening over the Pacific, where the warm waters slosh back towards the Eastern Pacific, and with it comes a massive rearrangement of the general circulation, and a warming signal is associated with El Nino. And so what it turns out is that when you plot the model temperature trend against that trend in the El Nino state, you see this nice correlation. So it means if a model is going a little bit more from an El Nino towards a La Nina state, it has a better chance to reproduce the observations. And the observational trend in the El Nino state are actually quite, again, far out of what models do. So internal variability could be an important factor why we have difficulties reproducing the observed temperature trends. So far, I've been talking about the ocean, but of course we live on land. And so the question was the impacts that we're interested in. Most of them are on land. So can we use that theoretical insights about internal variability, but also how kind of convection is tied to the warm end of the sea surface temperature distribution to make a statement about land? So now I have to be a little bit more precise, because up to now I've been talking mostly about temperature. But what we really mean is energy. And more precise, it's actually called so-called moist static energy, which is the sum of potential energy, which we can neglect here for the purpose of this talk. And then we have sensible heat, that is temperature, and we have latent heat, that's moisture. We can get away with temperature over the ocean because humidity is highly correlated with temperature. And so it's sufficient to talk about one. But this is not true over land. Think about the picture behind me. That's a desert. The temperature is very high, but the humidity is very low. For example, in contrast, Princeton in summer, you not only have warm, but you also have very high humidity. So that means over land, the humidity is not coupled directly to temperature. So we need to talk more precisely about energy or moist static energy. So the question or the hypothesis that Yi Zhang's PhD work is about was because of the smallness of the Coriolis term. So that's the Coriolis force that comes from Earth's rotation in the tropics. The troposphere in the tropics cannot sustain large temperature gradients, so that picture that I've shown you before of convection primarily over the warm and no convection over the cold waters should hold throughout the entire tropics to first approximation. That would also mean it should hold over land. And it would mean that in principle, we expect that the energy of storms over the Congo, over the Amazon, and over the Western Pacific Whirlpool should be very, very similar. So that's the hypothesis based on theory. And this is the data that we get, which confirms the theory. This is from a paper that Yi has written last year. And what it shows is as function of latitude on the x-axis, this moist static energy when we average it in longitude. So for simplicity, I'm not showing you a map, but I average it in longitude. So this is so-called zonal mean. And we do that separately for land and for ocean. And so the land here is the red line, and the blue is the ocean line. And you see they do not agree. However, when we do that only in the regions where we do have deep convection, you see this is what it looks like. It's completely uniform, and it's equal over land and ocean between about 20 south and about 20 north. The departure here, we will come back to that at the very last slide, is towards the subtropics. This assumption of the smallness of the Coriolis force is breaking down. But for about 20 south to 20 north, this works really beautifully. We can go into climate models and we see the same story. When you just average over land and ocean, you get a difference. Climate models have the advantage you can look into the future, so that would be a warmer prediction, or you can look back into what they simulate for the last glacial maximum. So it's also different. But again, when you look where the rainfall or the deep convection occurs, the theory holds for the future warm world, for the present, and for the past, for the last glacial maximum. And that is because the theory is not dependent on the temperature or the mean state of the climate. And so, in short, the point is there is good reason from a theoretical perspective that the model should do that. And we do not expect that when you go to better models with higher resolution, that these sort of insights would fundamentally change. With that, I come to the last part. Convection is one thing, so that's rainfall, that's really important. But Yi was interested also in the heat stress. So heat stress is a problem in the tropics. And so unlike right on the flyer here, that was a temperature signal. And temperatures tend to peak kind of where it's dry. So that's the Sahara here. But for heat stress, we really need to worry about humidity and temperature, because it can be very warm outside, but if the air around you is dry, you can sweat, and you have evaporative cooling. So you have two ways to get rid of your body heat. One is through simply the heat transfer, and the other is through evaporation. For evaporation, you also need a gradient between the saturation vapor pressure over your skin, so the temperature of your skin, and the specific humidity of the surrounding air. There is a quantity that expresses that concept. It's called the wet bulb temperature. But at sea level, this is essentially identical to the moist static energy that we've just been talking about, because it's exactly the same thing. You want to get rid of energy, so it's the total energy that matters. Moist wet bulb temperature is also an important part of an important kind of a heat stress metric that is widely used, sort of the wet bulb globe temperature. We have taken it because although it's less used for the direct physiological impact, it has this physical meaning. And so we can apply our insights that we have for the physical theory for the moist static energy, we can apply it to that wet bulb temperature. We also know, and that's kind of where the impact comes from, while we don't know if it's sort of 1 degree more or less, how much that would slow you down, but we know there is a limit. And if that wet bulb temperature gets above about 35 degrees Celsius, that is basically the deadly limit. if the surrounding air is exceeding that value, it means you cannot cool off your body heat anymore. And that, in the absence of other cooling, you would die. So this is a really serious problem. We already know, this is a figure from a paper a couple of years ago by Kofel et al. Simply kind of asking, where is this wet bulb temperature peaking? And this is a forecast for the future. And what you see here is it's really the low latitudes, right? And it's kind of what you expect. It's not the desert, because as I said, it's going to be hot there, but there is no humidity. So the problem is kind of where you have heat and humidity. So he put together this really beautiful hypothesis, or the reasoning is, the wet bulb temperature is closely related to most static energy. We have a theory for most static energy. We also have from observation that the leading mode in models, the observations we can discuss afterwards, but in model, the leading mode is a very uniform warming. So that means the warmest end is warming maybe a little bit more, but it's more or less scaling like the mean. Since the maxima are through convection coupled between land and ocean, we know that the maxima over land are equal to the maxima over the ocean. Since the maxima over the ocean scale like 1-to-1 with the mean, we know that also the maxima over land will scale like 1-to-1 with the mean warming. So he went and tested her hypothesis against data. And now came this really beautiful plot. What this shows is for 4 regions. You should see the maps here. So this is the Amazon rainforest. This is the maritime continent. This is the lower part of the Indian Peninsula, and this is the Sahel. What it shows is from a range of models that submitted their simulations for the next 150 years or so. Each model has a different warming. What we plot here is, as function of the warming that this model gives, the change in the extreme temperature. By extreme temperature, he took the daily average maximum of 1 year. If you do that, you get the red lines. The solid line is the multi-model mean, and the range is the range between different models. So what you see is you have that the warming, I also show you in black here, the 1-to-1 line. So the temperature is increasing in this region faster than the tropical average temperature. And the uncertainty here is really large. You can see some models give you about 4 kelvins more. Other models give you about 12 kelvins more. So if you're worried about impacts and you look at this, you should be very worried about the difference in model predictions, right? So here you have a 3 times more severe heat wave than here. If you look instead at what is really relevant, namely the wet bulb temperature, you see that all these differences fall back onto the 1-to-1 line, just like heat theory predicted. You also see that the range of differences is much, much smaller. And that is simply because if a model shows a large temperature increase, it tends to show a moisture decrease and vice versa. So the wet bulb temperature is much more constrained and much more precise and beautifully explains the extrema by theory. And this allows us now to make a statement about what we might expect. And that is the beauty about it. Anytime, anywhere in the entire 20 to 20 tropics for the future, for the most extreme sort of heat stress that we should encounter. Note, for that theory, we do not need to know the local conditions. There is no local weather going into the theory. With that, I'd like to close my talk and briefly summarize. As I said, what we have shown you, the importance of theory for kind of assessing whether something is a climate change and whether we believe it or whether we should be cautious about it. The beauty about this theory, as I said, is it allows you to make a statement about something that could happen anytime, anywhere, without knowing the local details. The Second thing that I brought up is internal variability is really a big issue at the moment. And we need to do more to sort out what exactly internal variability is doing. As said, the observations are the gold standard, and we now have about 40 to 50 years of satellite data. I dare to say that probably when people started making these measurements, they did not think that 50 years later we would still struggle about internal variability, because the idea probably was that after a couple of years, these things would sort of even out. But as it turns out, we're still fighting to detect climate changes in many, many variables, and a lot of it is due to internal variability. And with that, the last sort of cautionary note is that our theory applies to 2020 in the deep tropics. It does not apply sort of to the subtropics. And we know that the record heat stress, so for example, in Pakistan, so is just outside that region. We also now understand why that is so, exactly because the Coriolis force is getting larger there, so you can have departure from theory there. So we make no statement about what the extrema might be there. With that, I'd like to thank again my entire group over the last couple of years. And of course, I would like to thank you for your attention. And with that, I give the microphone back to Mike.
Thank you, Stephan, for a fantastic talk. Let me now bring in our discussant to coordinate the discussion and questions. It's Jim Smith, who's the William and Edna McAleer Professor in Civil and Environmental Engineering here at Princeton. Jim works broadly in the fields of hydrology and hydrometeorology with a focus on extreme events and also on measurement and modeling of rainfall. So Jim, thanks again for, as I said before, filling in on a sort of last minute request. And I turn the floor over to you, Jim. And Stephan, I remind everyone that if you want to send in questions, you use the Q&A box on your screen. Thank you.
Thanks, Mike, and Stephan, a very interesting set of ideas on climate change in the tropics, and a nice illustration of the power of combined theoretical climate modeling and observational attacks on high-profile climate change problems. Also, kudos to you on translating very important scientific results into a simple public messaging. So to you and Yi Zhang, that's I think an important element of the study that you've carried out. I'd like to kick off the discussion session with sort of a two-part question. You identify low clouds as one of the important actors in your analyses. Low clouds have received considerable attention and considerable controversy in recent climate change studies. So the two-part question is, on the first, could you emaborate on the role of low clouds in your assessments of change in extrema of wet bulb temperature? And then the second and broader question is, could you comment on the role of low clouds in uncertainties in climate modeling, and in particular how that relates to the types of problems that you've been attacking?
Yes, thank you very much for the question. So the first question was, how do the low clouds sort of affect the heat stress extrema, or sort of how they're coupled, right? And so I might have to clarify that the audience might think first sort of clouds, oh yeah, that might reduce my local heat stress, so that the solar insolation gets less. So the impact here is, as I said, is somewhat indirect. So typically where you have the low clouds, you're not struggling with heat stress. So the heat stress is really happening in the regions where you have the deep convection. And the connection comes about that if we have more or less low clouds, then the mean warming would be different. And so that is sort of basically the feedback that you would have. So we would have more extreme heat stress if we have less low clouds, because that would then be a positive feedback. So does that make sense? So in that sense, the connection is indirect, but I think the important thing is that kind of the point is that the change of the shape of the distribution function itself feeds back onto how much the mean is changing.
So this translates directly into assessments that have suggested that we may see rapid elimination of low clouds in some tropical regions. That just translates into the mean temperature analyses.
Yes, and so the question is, how well can we predict these clouds? And there are others that are more qualified to talk about that. But I would like to sort of just emphasize we typically rely on climate models that cover the globe to address this question. And they necessarily have to represent these clouds somewhat simplified. People have gone out and started so-called very high resolution radiative convective equilibrium simulation, or with a prescribed boundary condition, where you would have a small domain, but you can actually resolve convection, also the shallow convection. So you would have a resolution of a few meters or dozens of meters or kilometers. So you can do that for a limited domain. These simulations give us much more confidence in understanding what happens over that domain. The challenge that they have is that they have to prescribe what the large scale is doing. And so the coupling with what the large scale is doing and the small scale is still somewhat rudimentary. And I do hope that sort of, progress in numerical modeling is really rapid. And we probably will soon have the ability to sort of, do these global high resolution climate simulation, that we understand these coupling better and that the simulations will get better. I do think, however, kind of what we know from observations is that sort of the rough kind of dependencies that we evaluate, they're pretty robust. Something else that I'd like to sort of add here is one problem that we are dealing with is that a lot of studies are regional. And that is again, sort of what we also talked about in the heat stress. And I think more needs to be done in the integration of the regional changes into the global picture. Because very often what you see is spatial pattern shifts. So simply you see the large scale circulation is shifting around. And low clouds may suddenly disappear in one region. But if you look over the tropics as a whole, the cloudiness actually barely changes. And that is a really important message, is shifts in space often dominate the signal. And what you're not seeing is climate change, but you see a change in the spatial pattern. And this disentangling these processes is really important.
I guess another kind of broad question about the theoretical analyses. Could you step us through what the really key assumptions are that underlie the theoretical analyses that you've carried out?
So you mean of the changes in the extreme?
Yes, yes.
So I think I would like to sort of return that almost as a question to the audience, or as a brain teaser. It's actually, so what we have done is we have taken the observation that the sea surface temperatures evolve roughly without a change in the shape. Climate models do that. And what I pointed out is that the observations may show a deviation from it. Our theory then builds on this observational and modeling aspect. What is interesting, and what I would like to hope to continue working on in the coming years, is that we don't really have a theory in the first place. So the theory is incomplete of what the distribution should be in the first place. There's also a fair question whether this sea surface temperature distribution should actually stay sort of more or less invariant, or whether they should not. It's a modeling fact, but then we don't really have a very good answer to it.
Yeah.
And as I said, I would say that is kind of what we hope to do in the next few years.
Okay, a question from Mike McCracken. I'm just going to read this for you, Stephan. And it goes, you commented that wet bulb temperature changes are more robust indicators of change than temperature change alone, which can be quite variable. Have you generated global maps of near surface change and wet bulb temperature changes? And do these show much more even indications of change by latitude than is the case for the change in just temperature, which shows very strong Arctic amplification and relatively small warming in low latitudes? Related to this, do plots of change in wet bulb temperature show smoother patterns of change over the US than changes in just temperature? Did that come through reasonably clearly?
Yep, absolutely. So yes, we did plot maps, and basically the figure that I've shown you kind of is zooming in on these 4 regions. And the reason why I did not show the map is that these figures actually are even a more stringent test, because we take the maximum within that region and compare it. So a single day in a single location in that region, and compare it to what the tropical average is doing. And you get this extremely straight line, right? And so that, of course, then is holding at any given moment also to the map. Because as I said, we've basically taken the one point in the map that would be the furthest away from what you would expect. So with respect kind of to what happens then when you go further out, as I said, I really have to stress, this theory applies to about 20 south to 20 north. The nice thing about this is that this is the region where you're most worried about the wet, or basically about the heat stress. As soon as you go further out, the Coriolis force is becoming an issue, and the theory would break down, because what then basically gets lost is this global control, that basically you have a non-local control. It's always the maximum somewhere that sets the bar for everybody else. That is not true anymore in the mid and high latitudes. So this theory will not work at mid and high latitudes. So this is also not in that sense related to Arctic amplification, right? But again, it's a fair question. It's in sort of in the broader sense, it's the question of the mean and the extreme. You can exactly ask the same question. So we know that the temperature change when you look at the globe as a whole is not an even shift. So we have much stronger warming at the high latitudes. We do have some indication, but again, what is kind of missing kind of is this global theory that will predict how the shape of these distributions will change. And as I said, there's probably also not a single theory like you would have for the Planck spectrum, right? Because the processes involved are different. And so there's probably not a single theory that would explain you for the entire globe what's going to happen.
I'll follow up that a bit. So you've got 4 wildly different regions that you're looking at in the tropics, and the fact that they show really similar results is striking, and it points to sort of broadly, as you concluded, the weather side of things doesn't really matter. The question is, so taking the Sahel and the Amazon, the really 2 end members that you're looking at, if you dig under the hood, are there elements of the analysis that do in fact show some of this weather signal, or is it just really a clean representation of this mean scaling? And there, in part, you look at the maxima at a point over the entire domain. If you think over the entire region, are there some weather features, tied to some of the distinct geographic drivers of weather that come into play?
Yeah, so the idea is really that when we think about weather, so we have different weather. So we have fair weather, we have storms, etc.
Yeah.
The basic idea is that the storm weather operates under this global constraint, not the rest of the weather. As I said, we cannot make a statement about what it will do when we have no storm or when we are sort of in the dry period. We can only make a statement about what happens with the system when it is sort of at the maximum state. And that is kind of the importance to recognize here. So the weather, of course, is responsible for that maximum state. And it is energetically constrained. So the storm, the point is simply, it cannot build up more energy than what you have elsewhere. Because if it does so, then it basically surpasses what the bar that the other region has set, and it would immediately convect. And it then sets again the bar for everybody else. And so that is basically the mechanism. So we can make a statement about sort of the high end. It does not make a statement about all the rest of the period. And it does not make a statement whether the Sahel will get wetter or drier. Right? And that is sort of the important recognition, as that for example, the Amazon, we see a widespread between models. And that is because sort of the weather and then the mean climate in the Amazon evolves differently in these different models. So some models might have a substantial drying of the Amazons, others not. The important is that at the most extreme situation, you always have this deep convection happening. And this cannot escape the basically the global bar. And so in that sense, it's really trying to sort of bridge also the weather perspective with sort of this global perspective that we cannot predict the weather for every day, but we can make a statement about sort of the most extreme weather.
I was staring hard at the map that shows the number of days that increase above the mean. And it, for my friends in Tucson, it looks like they get about 100 days a year more, and Southern California the same. The final conclusion in your comments before, you suggest you get into the subtropics and everything breaks down with the theory. Now, does everything break down, or is there some way of looking at monsoon systems? Is there anything that you can recover to give our friends in Tucson some additional guidance on, they're worried, and how much they should be worried and how they should be worried?
Yeah, I think I'd like to sort of refrain from going out too far in the limb. Generally, I'd say kind of the region where we are most worried are probably sort of Arabian Sea, Pakistan, northern India, which is already now sort of a hot spot. Sort of it's a sweet spot because it is still in the tropics. It still has a massive insolation, but sort of the big temperature gradient of that is uniformity is starting to break down. And at the same time, sort of the mountains provide sort of somewhat the couching. So you don't have a lot of cold air outbreaks in that region. So, and at the same time, there's really a lot of people living there. So I think I'm most worried there. But as I'm not going to say anything about Tucson.
I know a lot of people that are concerned there, but I'll push you on another point. Now, you've really focused on the scientific side, yet there is this high-profile sort of public side of the result. Do you have any plans of structuring analyses that give more insight to this? The problem of heat stress in ways that the public health community would become even more engaged in this aspect of climate change in the tropics?
I think the simple answer directly is no. I would hope that Princeton is exactly the perfect place, and HMEI is the perfect place for that conversation, where we can bridge the more theoretical work that we do with sort of the impact community. I think there is a lot to be done in that direction, a better communication of understanding, but also kind of what to expect or not to expect. And as I said, I'm working more on the theoretical side, but I'm very open to anyone interested in a conversation. And I think this would be a splendid opportunity also for HMEI.
And Mike, turn it over to you.
I was going to say that sounds like the perfect time for me to jump in as Stephan suggests what we should be doing, which I agree. I think that this really has so much implication that it really is an interesting conversation. So anyway, but that's not my job for now. Unfortunately, my job is to keep time here. So let me again thank you, Stephan. I love the focus on sort of theory and precision, and I think it's just fantastic to have that as part of the conversation. So I really appreciate your presentation here today and the way you focus on these sort of important aspects of how we analyze, but also talk about climate change. And Jim, thanks to you as well for the terrific questions and discussions. I'll remind all of you, thank all of you for joining us. I'll remind you that we have one more lecture for this academic year. That will be next month in May with Reed Maxwell, who will be talking about water resources across the North American continent. So until then, I hope you all stay well, and I look forward to seeing you next month. Goodbye, everyone.